Today's topic of discussion is steam turbine and Rankine cycle system. So in this video, we will see the working principle of steam turbine and its association with power plant and Rankine cycle. So this is a typical construction of steam turbine. So the red line you can see, this is a nozzle, and we have rotating blades or moving blades fixed on the rotor, which is rotating. So these are the rotating blades, and we have also a stationary blade or fixed blade, which is acting as a nozzles and which is fixed to the casing. So steam comes axially here and goes out, and in between there are a number of stages where expansion of steam occurs in the steam turbine. So now a steam turbine is a machine used for power generation. You can see the configuration of a steam turbine here. A steam turbine, as the name suggests, uses high pressure and temperature, that is superheated steam, as inlet, and it gets expanded in the turbine. Low pressure and low temperature steam comes out from the turbine discharge or exhaust. The process of expansion of steam in the turbine is considered as an isentropic expansion process, where entropy of steam remains constant. A steam turbine can be used as a power generation as well as driver to drive the compressor and pump, etc. When used as a power generation, steam at turbine outlet is condensing type, where pressure is slightly lower than atmospheric, that is vacuum. Heat is removed in the condenser installed at turbine outlet. Outlet of condenser comes to the pump, suction as a water, because the steam has now converted into water, where pump makes higher pressure to the feed back to boiler for steam generation. In case of a steam turbine used as a driver, turbine outlet steam is lower pressure but non-vacuum and non-condensing type condition of the steam, and which can be used in the plant process application. As the expansion of steam occurs in the steam turbine, so a steam condition at turbine inlet should be superheated. Superheated steam, that is high temperature steam, at turbine inlet is required due to fact that when the expansion occurs, there is a drop in temperature. And so higher temperature at inlet is a must to avoid liquid formation or condensations in the blade, and which is a detrimental for the machine. Now a steam turbine classification, and it is done in two ways. One is based on application, another is based on the construction. So as per the application, turbine is classified in two categories. One is called condensing type turbine, another is a back pressure turbine. In case of condensing type turbine, which is mostly used for the power generation, and outlet pressure or exhaust pressure is in the partial vacuum. This is for mostly condensing type turbine. And back pressure turbine used as a driver for compressor and pump, etc. Outlet pressure, that is exhaust pressure, is lower but is still in a superheated condition and above the atmospheric pressure, and outlet pressure is used in the process plant application. Other features of a steam turbine are extraction type. In this feature of turbine, steam is taken from the various section of turbine at different pressure for industrial application. Power generation is lesser due to less steam available for the downstream stages. Extraction of steam is done to get the different pressure of steam, like high pressure steam, that is HP steam, medium pressure steam, that is MP steam, and low pressure steam, that is LP steam, because these type of steams conditions are required for the plant application. And reheat application or reheat feature, in this feature of turbine, Steam from the high pressure section of turbine is taken out and feed back to boiler for heating, that is superheated, and then comes to the intermediate section of turbine. This is done to avoid the condensation in the last stage of the blade. This is used for power generation application. Now ranking cycle for condensing type turbine. So you can see this. This is a steam turbine. This is a condenser. This is a pump, feed water pump, and this is a boiler or a steam generator. So the process 1 and 2, that is 1 and 2 process, isentropic or adiabatic expansion in the turbine. This is process 1 and 2. Process 2 and 3 is a constant temperature, that is isothermal, and constant pressure, isobaric, that is constant pressure, heat rejection in the condenser, process 2 and 3. And process 3 and 4 is a constant volume, that is isochoric, compressor of pump, that is pressure rise occurring of the pump from 3 to 4 by the feed water pump. This is liquid state. Now process 4 and 5, that is constant pressure, that is heat addition in the steam generator, that is 4 to 5. Then process 5 to 6, 5 to 6 is a constant temperature and constant pressure heat addition, that is evaporation in the steam generator or boiler. And process 6 to 1, that is 6 to 1, is the constant pressure heat addition, that is superheated steam in the steam generator or boiler. So these are the processes for Rankine cycle. There's another view we can show in the Rankine cycle on pressure versus volume diagram. X-axis is volume and Y-axis is pressure. So same process is shown in another form, that is PV diagram. Process 1, 2 is the isentropic expansion in the turbine. Process 2 and 3 is a constant temperature, constant pressure, heat rejection in the condenser. Process 3 and 4 is a constant volume, pressure rise occurs in the feed water pump. And process 4 and 5 is a constant pressure heat addition in the boiler or heat generator, steam generator. Process 5 and 6 is a constant temperature, constant pressure heat addition in the boiler. And process 6 and 1 is a constant pressure heat addition, that is superheated steam in a steam generator. So this is Rankine cycle on PV diagram. Now there is another application, that is a Rankine cycle for a back pressure steam turbine. So in this cycle, the process 1, 2 is a isentropic expansion in the turbine, and then it goes to the plant process. And process 3 and 4, for this we need a separate DM water available, and so that through the feed water pump the pressure rise occurs from 3 and 4, then at a constant volume. Then process 4 and 5 is a constant pressure heat addition in the boiler, and process 5 and 6 is again constant temperature and constant pressure heat addition, that is evaporation in the boiler or steam generator. And process 6 and 1, that is constant pressure heat addition, that is a superheated steam in the steam generator. The only difference between the condensing and non-condensing that the from point 2 and 3 is not connected in the back pressure, whereas in condensing 2 and 3 are connected. This can be also shown on the PV diagram. So process Rankine cycle, the process 1 and 2, that is a isentropic expansion in turbine, and then it goes to plant process. Process 3 and 4 is a constant volume, pressure rise occurs of by the feed water pump. Then process 4 and 5 is constant pressure heat addition in the steam generator. Process 5 and 6 is a constant temperature, constant pressure heat addition, that is evaporation in the steam generator. And process 6 and 1 is a constant pressure heat addition, that is superheated steam in the steam generator. So this is another way to show the back pressure Rankine cycle on PV diagram. Now, steam turbine classification based on the construction. Broadly, it has two section or two categories. One is called impulse turbine, another is impulse and reaction turbine. In case of impulse turbine, it has a two subcategory, that is what constant, pressure compounding turbine. This is impulse turbine, and velocity compounding turbine. This is again impulse turbine. In case of impulse turbine, that is a pressure compounding, we have single stage impulse turbine, that is a D level and ratio of single stage. And then multi-stage impulse turbine is a ratio turbine. Impulse turbine velocity compounding is a impulse turbine, that is Curtis wheel turbine, and impulse reaction turbine is a multi-stage impulse reaction turbine, that is a Parsons turbine. So I hope you have enjoyed and understood the basic working principle of a steam turbine and Rankine cycle, broadly how the Rankine cycle are used for the condensing and non-condensing applications, and the classification of steam turbine. So thank you for watching.